September 16, 1943. Bougainville, Solomon Islands. First Lieutenant Kenneth Walsh examined his hand as he made notes in his flight journal, recording what would become a defining moment in Pacific aerial combat. "This new aircraft changes everything," he wrote. "Speed and firepower grant us advantages the Zero can't equal. What we need now is greater precision in deflection shooting." Through the scuffed plexiglass of his F4U Corsair's canopy, Walsh had just returned from escorting Navy bombers, observing the difficulties that even seasoned aviators faced. Striking a maneuvering opponent while both planes twisted violently through the sky demanded calculations that human reflexes could barely complete in fractions of a second. What Walsh and thousands of other Marine and Navy pilots could not yet realize was that British engineers had already devised a solution. A device using spinning gyroscopes and finely tuned mirrors would soon revolutionize aerial gunnery, transforming it from an art requiring years of experience into a science learnable in mere weeks. The Mark 18 gyroscopic gunsight would reach the Pacific theater within a year, fundamentally changing the mathematics of air combat. The Vought F4U Corsair had entered battle in February 1943, bringing unmatched speed and firepower to marine aviation. Powered by the Pratt & Whitney R2800 double wasp engine generating over 2,000 horsepower, the Corsair could exceed 400 miles per hour, making it the first American single-engine fighter to cross that threshold. Its 6 Browning M2 machine guns, each firing 50 caliber rounds at nearly 800 per minute, unleashed devastating power when rounds found their mark. The difficulty lay in making those bullets connect. Deflection shooting, the craft of hitting a moving target from a moving platform, represented the single greatest challenge of dogfighting. When a Corsair flying 400 mph fired at a Zero twisting away at 300 mpq, the pilot had to aim not at the enemy's position, but at where the aircraft would be when the bullets arrived. Those projectiles, leaving the barrels at about 2,700 feet per second, still took time to travel. At 500 yards, the delay approached half a second. In that brief instant, a Zero in a standard turn could move nearly 200 feet. The pilot had to lead by precisely that distance, constantly adjusting as ranges and angles shifted, all while enduring G-forces that blurred vision and made mental computation impossible. The Mark 8 reflector sight. Standard equipment on Corsairs through 1943 and early 1944 offered no help with this problem. It merely projected a glowing reticle onto a glass plate, a fixed point showing where the guns were aimed. Pilots estimated the proper lead entirely by intuition and practice. Skilled flyers developed a sense for it after countless missions. Many never did, wasting ammunition that vanished harmlessly into the Pacific. Lieutenant Kenneth Walsh, serving with VMF 124, had mastered deflection shooting through relentless repetition and innate skill. On May 13, 1943, he became the first Corsair ace after downing 3 Japanese fighters, bringing his total to 6 confirmed kills. Walsh learned to anticipate motion, sense the right lead, and fire at the instant when instinct and geometry aligned. His success came from hundreds of flight hours and a natural grasp of three-dimensional movement. Most pilots lacked that intuition. The typical Marine aviator reached combat with perhaps 200 total flight hours and barely 20 devoted to gunnery, usually against towed targets flying straight and level, not against agile Zeros flown by veteran Japanese aces. Average pilots struggled to hit anything. Reports from 1943 reveal that many expended every round without scoring a single victory, their shots missing by fractions of a second. The British had identified this flaw early. In 1941, Ferranti began producing the MK2 Gyro-Sight, a groundbreaking instrument that used rotating gyroscopes to automatically compute deflection angles. The concept was elegantly simple. Gyroscopes resist changes in orientation. When the aircraft turned, the internal gyros stayed pointed in their original direction as the plane moved around them. By measuring that resistance through gears and mirrors, the sight calculated the rate of turn, and thus the required lead angle. The sight then adjusted the reticle automatically, placing it precisely where the pilot needed to aim. Royal Air Force pilots using the Mk2 gyro sight reported remarkable improvements. Spitfire pilots who once struggled suddenly found themselves scoring hits with their first bursts. The device removed the need for complex mental math, freeing pilots to focus on tactics and positioning. The United States quickly recognized the technology's potential and contracted the Sperry Gyroscope Company to manufacture American versions. The U.S. Army Air Forces designated theirs the K-14, while the Navy and Marine Corps adopted the Mark 18. Both were nearly identical to the British model, with minor adaptations for American production and cockpit layouts. Sperry's massive facility at Lake Success, New York, employed over 20,000 workers at peak output, producing gyroscopic gun sights alongside bomb sights, fire control systems, and navigation equipment. The Mark 18 was significantly bulkier than the simple reflector sight it replaced. Where the Mark 8 was a compact unit weighing perhaps 5 lb, the gyroscopic sight system weighed 12 lb and required significant cockpit modifications. Sperry engineers explained that the bulk was necessary. Inside the housing were two independent gyroscopes measuring pitch and yaw, spinning continuously once powered. These gyroscopes contained the secret to solving deflection shooting, the single most difficult aspect of aerial gunnery that had challenged fighter pilots since the First World War. The Mark 18's design incorporated lessons learned from British combat experience. The sight featured two independent reticles visible to the pilot. On the left side, a fixed cross indicated where the guns were actually pointed, providing a reference for the aircraft's bore axis. On the right side, a gyro-stabilized reticle consisting of a center circle surrounded by 6 diamond-shaped pips showed the computed aiming point. As the pilot maneuvered to track a target, the gyroscopic reticle automatically positioned itself ahead of the enemy aircraft by exactly the correct lead angle. The pilot's procedure simplified dramatically compared to reflector sight operation. First, he set the target's wingspan using a control on the sight itself, selecting from known values for Japanese aircraft types. The A6M0, most common opponent in the Pacific, had a wingspan of 36 ft for standard variants. With wingspan selected, the pilot adjusted a twist grip integrated into the throttle lever to expand or contract the diamond-shaped ranging reticle until it matched the apparent wingspan of the target as seen through the sight. This action mechanically set the range, informing the sight's ballistic computer how far away the target was and therefore how much bullet drop to compensate for. With range and wingspan set, the gyroscopes took over. As the pilot maneuvered to track the target, the moving reticle automatically positioned itself ahead of the enemy aircraft by exactly the correct lead angle for the current rate of turn. The pilot simply had to place that computed reticle on the target and press the trigger. The bullets would arrive precisely where the sight predicted, regardless of the complexity of the maneuvering production of the K-14, and Mark 18 began in earnest during spring 1944. The U.S. Army Air Force received priority for European theater, operations with P-51, Mustangs, and P-47, Thunderbolts receiving K-14 installations beginning in August. 1944, the Navy and Marine Corps followed, closely with F4U Corsair and F-6F Hellcats scheduled for Mark 18, retrofits through fall and winter 1944. The first Corsair squadrons to receive the Mark 118 were those preparing for carrier operations. VMF-124 and VMF-23, the first Marine fighter, squadrons assigned to fleet carriers, received their gyroscopic sights during training at Naval Air Station Santa Barbara in late 1944. The squadrons would join USS Essex in December, bringing the Corsair into carrier-based combat for the first time. Lieutenant Robert McClure, flying with the reformed VMF-214, received his Mark 18-equipped Corsair in early 1945. McClure had scored several victories during 1944 using the standard reflector sight, but he immediately recognized the gyroscopic sight's revolutionary potential. In a letter to his family, later preserved in Marine Corps archives, McClure wrote that the Mark 18 represented the difference between skilled guesswork and mechanical certainty. The device compressed years of experience into a few hours of training. Japanese naval aviation intelligence first became aware of American gyroscopic gunsight technology in late 1944 through analysis of recovered Corsair wreckage and interrogation of captured documents. What they discovered alarmed them profoundly. Technical specifications confirmed that Americans had developed a fire control system that largely eliminated human error in deflection shooting. Japanese tacticians understood immediately that this technological advantage could not be countered through improved training or modified tactics. The mathematical precision of gyroscopes spinning thousands of times per minute could not be matched by human reflexes, no matter how experienced the pilot. Japanese fighters had survived thus far by exploiting their superior maneuverability to force American pilots into difficult deflection shots where human calculation errors provided some margin of safety. Against Mark 18-equipped Corsairs, that margin vanished. Any American pilot who could track a Japanese fighter long enough to set range would score a hit regardless of the complexity of the maneuvering involved. Tactical modifications were ordered across all Japanese naval aviation units. Japanese fighters were instructed to avoid prolonged turning engagements with Corsairs at all costs. The new doctrine emphasized hit-and-run attacks, diving from altitude to make a single pass before extending away at maximum speed. This tactical shift acknowledged an uncomfortable reality that Japanese pilots could no longer rely on maneuverability alone to survive against technologically superior gun sights. December 1944 brought a significant milestone in Corsair operations. VMF-124, commanded by Major William Geyser, became the first Marine fighter squadron to operate from a fleet carrier when they joined USS Essex at Yulee. VMF-203 joined simultaneously, bringing 48 F4U Corsair to carrier operations. Both squadrons were equipped with Mark 18 gyroscopic gun sights, representing the cutting edge of American aviation technology. The Essex Air Group sorted in January 1945 for strikes against Formosa and the Philippines. Marine Corps air pilots flew combat air patrol, bomber escort, and strike missions, finally bringing the F4U into the carrier-based role for which it had originally been designed. The Mark 18 proved invaluable during these operations. Pilots engaging Japanese interceptors reported significantly improved hit rates compared to their previous experiences with reflector sights. Combat action reports from January and February 1945 document numerous instances where pilots achieved kills with their initial burst, a level of first-pass success that had been uncommon with earlier sighting. Systems. The difference was most apparent. During bomber escort missions where Corsairs maintained formation, positions that often prevented ideal attack geometries. The Mark 18's ability to calculate accurate deflection from any angle transformed these constrained engagements into opportunities rather than disadvantages. Pilots no longer needed to maneuver into perfect zigzag positions. They could engage from deflection angles that would have been impractical with reflector sights. February 1945 brought the invasion of Iwo, where Marine Corsair provided continuous air cover for the assault force. Multiple Marine squadrons flew from escort carriers, maintaining combat air patrols over the invasion fleet and supporting ground operations. The Mark 18 equipped aircraft demonstrated their effectiveness during defensive missions against Japanese air attacks. Pilots intercepting incoming raids consistently achieved kills at ranges and angles that would have been difficult with older sighting. Systems. The gyroscopic sight's automatic deflection calculation allowed pilots to engage multiple targets in rapid succession. Where a pilot with a reflector sight might have expended all ammunition on a single difficult target, Mark 18 equipped pilots could achieve hits on 2 or 3 targets during the same engagement, conserving ammunition and multiplying their effective combat power. Squadron commanders noted in operational reports that less experienced pilots were achieving combat effectiveness comparable to veterans, primarily due to the improved fire control provided by the gyroscopic sight. March 1945 saw the continuation of carrier operations against the Japanese home islands. VMF 2114 aboard USS Franklin participated in strikes against Japanese airfields and installations. On March 19, 1945, Franklin was hit by a Japanese bomber while operating off Kyushu. The resulting explosions and fires killed over 700 men aboard the carrier, including 32 members of VMF 214. The squadron suffered devastating casualties, but the survivors continued operations after the Franklin limped to safety. The disaster highlighted both the dangers of carrier aviation and the courage of the pilots who flew these missions. Despite the losses, Marine Corsair squadrons continued their mission, providing air cover and strike capability for the fleet. April 1945 brought Operation Iceberg, the invasion of Okinawa. This campaign would witness the most intensive kamikaze attacks of the war, with Japanese forces throwing thousands of aircraft against the American fleet in desperate attempts to halt the invasion. Marine Corsairs equipped with Mark 18 sights played a crucial role in defending against these attacks. The gyroscopic sight proved particularly effective against kamikaze aircraft, which flew predictable attack profiles that made range, estimation, and deflection calculation. Straightforward pilots could acquire incoming kamikazes, set range using the sight's ranging reticle, and achieve first-burst hits with regularity that would have been impossible with reflector sights. Combat air patrol missions during April through June 1945 resulted in hundreds of Japanese aircraft destroyed. While precise data specifically crediting aerial victories to Mark 18-equipped aircraft versus those using reflector sights is not available in declassified archives, combat reports consistently noted enhanced effectiveness. Among squadrons equipped with the gyroscopic sight, the psychological effect on Japanese pilots who survived encounters with Mark 18-equipped Corsairs went beyond a simple tactical setback. The experience of being struck despite evasive maneuvering, of watching tracers bend through the sky with uncanny precision, created a sense of technological futility that traditional training had not prepared them to face. Post-war interviews with Japanese airmen revealed that many regarded advanced American fire control systems as among the most discouraging technologies they encountered. The near certainty of being hit once an American pilot achieved a tracking solution destroyed the confidence that had sustained Japanese fighter pilots in increasingly hopeless circumstances. Agility could no longer save them. Experience offered no real advantage, and the only escape was to avoid combat entirely, an impossible tactic when defending bombers or fleet assets. The Mark 18's internal workings represented a remarkable feat of mechanical computation. It functioned without electronics, relying on a network of gears, linkages, and mirrors to execute calculations that would challenge a skilled mathematician. The gyroscopes spun continuously once powered, maintaining spatial orientation through angular momentum. As the aircraft turned, the gyro housings rotated relative to the fixed rotors. Precision mechanisms translated that movement into mirror adjustments that shifted the aiming reticle. The entire system operated within tolerances measured in thousandths of an inch. Manufactured using the most sophisticated machining processes available in 1944, Sperry's production facilities stood at the summit of American precision engineering. Each Mark 18 required numerous components machined to rigorous specifications. The gyroscopes themselves were miniaturized marvels, their bearings designed to function smoothly under sustained high-G maneuvers without friction or failure. Rigorous quality control testing ensured each site met performance standards before delivery. Test rigs simulated flight maneuvers to verify that the site calculated deflection angles correctly across multiple ranges and turn rates. Any unit that failed was recalibrated or rebuilt. The challenge was not merely producing the sights, but producing them in quantities sufficient to equip thousands of aircraft across multiple fronts. Sperry ramped up output throughout 1944, training workers in the delicate arts of optical and mechanical assembly. The Mark 18 benefited from American mass production methods while preserving the exacting standards required of a precision device. Parts were designed to be interchangeable, allowing assembly from components made at separate factories. This modular approach also simplified field maintenance. If a site failed in service, technicians could replace specific modules instead of the entire unit. Spare components were stocked across the Pacific, minimizing downtime for combat aircraft. Integrating the Mark 18 into Corsair cockpits demanded careful ergonomic planning. The sight had to be positioned for clear visibility without obscuring situational awareness. The range adjustment on the throttle had to be within reach without forcing the pilot to release flight controls. Engineers collaborated with seasoned pilots to refine placement, incorporating combat feedback to reduce distractions during intense engagements. The result was a system that could be operated instinctively, without diverting attention from tactical decisions. Training programs were developed to ensure pilots could employ the Mark 18 effectively. Instruction emphasized interpreting the sight's indications and recognizing when it had stabilized after abrupt maneuvers. Pilots learned when to rely on the computed reticle and how to set range quickly using the distinctive diamond pattern. Ground training covered the fundamentals of gyroscopic computation without overwhelming students with mathematical detail. The goal was operational mastery, not theoretical knowledge. Flight training included live intercepts to let pilots observe how the sight performed under real conditions. Instructors stressed smooth pursuit, as erratic movement could temporarily disrupt accuracy. The gyroscopes required several seconds to restabilize after violent maneuvers. Skilled pilots learned to anticipate this lag and timed their attacks accordingly. Despite such minor constraints, the Mark 18 represented a transformative leap in fire control capability. Pilots who had once struggled with deflection shooting found themselves scoring hits with consistency that had seemed unattainable. The sight did not make air combat easy, but it removed one of its most unforgiving variables. The total impact of the Mark 18 on Corsair performance in 1945 remains difficult to quantify precisely. Official statistics record that the F4U Corsair achieved an overall kill ratio of 11.1 during World War II, 2,140 victories against 189 losses over 64,051 sorties. These totals include aircraft with both reflector and gyroscopic sights. Isolating the Mark 18's specific contribution would require detailed combat records that remain classified. Yet, pilot testimony from those who flew with both systems is unanimous. The Mark 18 made deflection shooting more consistent and less dependent on raw talent. Evidence from squadron records and memoirs confirms the gyroscopic sight provided tangible advantages in battle. The Mark 18 program embodied the height of American industrial and technological strength, integrating advanced gyroscopes, optical, precision, and mechanical computation into a compact, combat-ready instrument. It was produced in vast numbers, maintained under rugged conditions, and delivered worldwide through a robust supply network. The program's success stemmed not from one single breakthrough, but from the entire system functioning in harmony. British scientists conceived the principle. American engineers refined it for mass production. American factories built it at scale, and American logistics ensured it reached the front lines. In the years following the war, Japanese aviators reflecting on Allied fire control systems concluded that by late 1944 and early 1945, American gunnery technology had rendered traditional Japanese air combat tactics effectively obsolete. The maneuverable fighter, piloted by well-trained aviators, could not compete against aircraft equipped with systems that calculated deflection automatically. Japanese post-war aviation development reflected these lessons learned. The Japan Self-Defense Force, established in the 1950s, emphasized advanced avionics and weapon systems over aircraft maneuverability. The pilots who had survived combat against Mark D-18 equipped Corsairs understood that future aerial warfare would be decided primarily by technology rather than individual skill alone. The Corsair itself continued in service long after World War II ended. Mariner squadrons flew F4Us during the Korean War from 1950 to 1953, providing close-air support for ground forces and flying interdiction missions. Many of these aircraft retained their Mark 18 gyroscopic sights throughout their operational lives. The technology that seemed revolutionary in 1944 had become standard equipment by 1950, unremarkable and expected. This normalization of technological sophistication characterized the post-war era. Capabilities that would have been considered impossible in 1940 were routine by 1950 and obsolete by 1960. The transformation of aerial gunnery from art to science, accelerated by the Mark 18's introduction, reached its logical conclusion with guided missiles that required no pilot aiming whatsoever. Air-to-air missiles, first deployed operationally in the 1950s, eliminated even the requirement that a pilot maneuver his aircraft to point his weapons at the target. The progression from reflector sights to gyroscopic sights to radar-guided missiles occurred in less than 15 years, a pace of technological change unprecedented in military aviation history. By the time American pilots flew missions over Vietnam in the 1960s, the Mark 18's gyroscopic principles had been incorporated into far more sophisticated fire control computers. These systems integrated radar ranging, automatic lead computation, ballistic calculation, and target identification into unified packages that bore little resemblance to the mechanical computer of 1944, yet the fundamental principle remained identical to what the Mark 18 had pioneered. Measure the platform's motionlessing gyroscopes, calculate the required lead angle, and present that information to the pilot in a form that made accurate shooting possible. The statistical record of World War II Corsair operations provides context for understanding the Mark 18's role in Pacific Air Combat, Marine, and Navy Corsair. Squadrons flew tens of thousands of sorties against Japanese forces from 1943 through 1945. They achieved the 11-1 kill ratio that established the Corsair as one of the war's most successful fighters. This success resulted from multiple factors working in combination. The Corsair's speed advantage over Japanese fighters allowed pilots to control engagement geometry, choosing when to fight and when to disengage. Its rugged construction meant it could absorb battle damage that would have destroyed lighter Japanese aircraft. Its heavy armament delivered overwhelming firepower when bullets connected with targets. The Mark 18 gyroscopic sight amplified these existing advantages by making it easier to deliver the Corsair's firepower accurately. The sight didn't create the Corsair's superiority, but it enhanced what was already a formidable weapon system. Pilot quality remained crucial. The Mark 18 helped pilots shoot accurately, but it didn't teach them tactics, situational awareness, or judgment. These skills still required experience and training. What the sight did was compress the learning curve for one specific skill, deflection shooting, that had previously required extensive practice to master. The broader historical context reveals that the Mark 18 was one component of comprehensive American technological superiority in the Pacific War. Radar systems provided early warning and intercept control. Radio communications enabled coordinated operations. Proximity-fused anti-aircraft shell-screeded defensive envelopes around ships. Each technology individually provided advantages. Together, they created a synergistic system that Japanese forces could not match. The Mark 18 fit into this larger pattern. It wasn't a wonder weapon that single-handedly won the air war. It was a practical improvement in fire control that made already effective aircraft more effective. Its contribution was incremental rather than revolutionary. But that incremental improvement, multiplied across thousands of aircraft and tens of thousands of combat engagements, produced significant cumulative effects. The legacy of the Mark 18 extended beyond its direct combat application. The sight's development required unprecedented collaboration between scientists, engineers, and combat pilots. Theoretical physics-informed gyroscope design, manufacturing engineers solved production challenges, and pilot feedback drove iterative improvements. This collaborative approach became a model for future weapons development. The procurement process also established precedents. Rather than developing entirely new technology from scratch, the United States recognized British innovation and adapted it for American production. This willingness to adopt foreign technology when it offered advantages demonstrated pragmatism that served American military aviation well throughout the Cold War and beyond. The manufacturing techniques developed for Mark 18 production had lasting impact beyond the specific device. Sperries. Modular assembly processes where different facilities could produce interchangeable subcomponents enabled the massive production volumes that gave American forces their technological edge. Similar techniques were later applied to radar systems, aircraft engines, and eventually electronics, creating an industrial base capable of producing complex precision equipment at scales impossible for other nations to match. The pilots who flew with Mark 18 sights formed a unique generation, transitioning from instinctive gunnery to more systematic technology as assisted combat. Many continued military careers, flying jets in Korea and serving in staff positions where they shaped tactical doctrine around the capabilities that advanced fire control provided. Lieutenant Kenneth Walsh, who had become the first Corsair ace in 1943 using only a reflector sight and natural ability, ended the war with 21 confirmed victories. He received the Medal of Honor for actions on August 15, 1943, when he attacked a superior force of Japanese aircraft despite damage to his own Corsair. Walsh survived the war and remained in the Marine Corps until his retirement, eventually reaching the rank of lieutenant colonel. His career spanned the transition from instinctive aerial combat to technology-assisted engagement, from aircraft armed with machine guns to those carrying guided missiles. Walsh's experience represented the broader transformation of aerial warfare during the mid-10th century. Lieutenant Robert McClure, who flew with the reformed VMF 214 in 1945, survived the war with 7 confirmed victories. He remained in the Marine Corps until 1965, retiring as a colonel. In his retirement, McClure wrote about the technological transformation he had witnessed. He emphasized that while the Mark 18 made deflection shooting more reliable, it never made aerial combat safe or easy. The sight eliminated one variable in the combat equation, but countless others remained: altitude management, energy state, situational awareness, tactical positioning. A pilot with a perfect gun sight could still be outmaneuvered, outclimbed, or simply caught unaware by an enemy he never saw coming. The technology improved effectiveness within engagements, but did not guarantee survival. The story of the Mark 18 concludes not with dramatic endings, but with gradual evolution into more sophisticated systems. As jets replaced propeller-driven fighters in the 1950s, new fire control systems replaced gyroscopic gun sights. The Mark 18 didn't suddenly fail or become worthless. It simply became outdated as faster aircraft and longer engagement ranges required more sophisticated solutions. Some Mark 118 sights remained in service aboard Corsairs flying close air support missions in Korea. Others were placed in storage or scrapped as aircraft were retired. A few were preserved in museums where they remain as tangible links to an era when mechanical computing represented cutting-edge technology. The Mark 18's legacy lives on not in physical devices which are now museum pieces, but in the principles they demonstrated and the technological lineage they initiated. Every modern fire control system, no matter how sophisticated, traces intellectual heritage back to devices like the Mark 118 that first solved fundamental problems of automated aiming. The engineers who worked on the Mark 118 contributed to knowledge that extends far beyond their specific technical achievements. They demonstrated that complex calculations could be performed mechanically with sufficient reliability for combat use. They proved that human-machine interfaces could be designed for operation under extreme stress. They showed that sophisticated technology could be manufactured at scale and maintained under field conditions. The pilots who flew with Mark 18 sights contributed their own legacy. They tested the technology under combat conditions and provided feedback that refined its design and operation. They developed tactics that exploited the sight's capabilities. Most importantly, they proved that humans could effectively partner with automated systems, neither becoming completely dependent on technology nor rejecting it as unnecessary. This balanced approach to human-machine teaming remains relevant as automation extends into more domains. The Mark 18 era offers historical examples of how such partnerships can succeed and what factors contribute to effectiveness. The Mark 18 gyroscopic Gunsight deserves remembrance not because it was revolutionary or because it single-handedly changed the Pacific War. It deserves remembrance because it exemplifies the less dramatic, but ultimately more important work of solving practical problems effectively in an era that often celebrates breakthrough innovations and disruptive technologies. The Mark 18 reminds us that incremental improvements, when implemented systematically at scale, often prove more valuable than revolutionary changes that cannot be produced or deployed effectively. The device succeeded because it was practical, reliable, and adequately effective. These characteristics, while perhaps unglamorous, define technology that actually makes a difference in the real world. The Mark 18 story is ultimately a story of people solving problems. Engineers designed it, workers constructed it, logistics teams transported it, technicians ensured its functionality, aviators employed it skillfully, and commanders incorporated it into effective missions. Every group provided vital contributions. Without any one of them, the program would have collapsed. This cooperative essence of technological achievement deserves recognition. Individual brilliance is important, but coordinated effort among countless individuals and organizations matters even more. The Mark 18 emerged from thousands of people performing their duties efficiently and diligently. That shared endeavor, more than any single act of genius, determined its success. The final evaluation of the Mark 18's influence must recognize both the verified facts and the lingering uncertainties. Official documentation confirms that the device was manufactured in large quantities, outfitted numerous Corsair and Hellcat squadrons throughout 1944 and 1945, and received positive feedback from the aviators who relied on it. Combat records indicate enhanced precision and shorter engagement durations among units equipped with gyroscopic sights. Pilot accounts consistently portray the Mark 18 as a major improvement over traditional reflector sights for deflection shooting. What cannot be precisely measured from available declassified materials is the exact numerical gain in kill ratios directly due to the sight versus other factors such as pilot proficiency, tactical evolution, or the diminishing effectiveness of Japanese opposition. The overall Corsair kill ratio of 11.1 reflects results across the entire conflict and encompasses both sight types. What remains evident is that the Mark 18 represented a substantial leap forward in fire control technology, providing tangible benefits to those who used it. It symbolized American industrial strength, creative innovation, and methodical problem-solving. At a time when aerial combat was evolving from pure pilot skill to system-based warfare, the Mark 18 marked a crucial transition toward the automated weapon systems that would shape post-war aviation. The device was successful because it performed dependably in combat, could be mass-produced efficiently, and was simple enough for pilots to operate without complex training. These functional qualities mattered more than theoretical sophistication or elegant design. The Mark 18 was built to address one core challenge, striking agile targets in high-speed combat, and it fulfilled that purpose effectively, remaining in service through the Korean War as proof of its enduring worth. For Corsair pilots flying with the Mark 18 in 1945, it was simply a reliable instrument that made an extremely demanding task a bit more manageable. It didn't remove danger or ensure safety, but it improved survival odds in battles where margins were razor-thin and outcomes unpredictable. In the broader story of technological progress, The Mark 18 gyroscopic gunsight stands as a bridge between the age of instinctive aerial gunnery and the dawn of radar-guided weaponry. It demonstrated that machines could compute faster and more accurately than human intuition, a concept that would transform aviation and extend far beyond the battlefield. The pilots who experienced this evolution understood that they were witnessing a technological revolution that would permanently reshape air combat. The Mark 18 was both a conclusion and a beginning, the peak of mechanical fire control and the foundation for the electronic systems that followed. Its legacy endures in the targeting computers of today's aircraft, advanced descendants of those first spinning gyroscopes that taught machines how to aim. The story of Japan never anticipating that Gyro Gunsights would turn Corsair pilots into marksmen is a tale of necessity driving innovation, of engineering meeting warfare, and of invention becoming application. It is the story of how American industrial strength and systematic ingenuity revolutionized air combat in the Pacific, one spinning gyroscope at a time.